Okay, let's get started today. So we are embarking on a new section of the course today. Today and for the rest of the semester, we'll be talking about data structures that allow us to organize data so that we can support the following three operations efficiently. Find, insert, and delete. Okay, so an emphasis here on efficiently, to find elements of data, to insert new elements of data into a data set, and to delete. So to find, insert, delete items in a data set. And an important element here is that the size of the data set is dynamic, meaning that it's not fixed when it's first read in. In CS102, we gave you an example of using an array and binary search, and that was an efficient way to search a data set when the size of the data set was fixed and there were no insertions and deletions. For those of you who don't remember binary search, the idea was that you sorted your data set elements, and if you were looking for something, does anyone remember what the first element was that you would look for? Where roughly in the array would be the first element? The middle element. So it would be 5 divided by 2, or the first element you would look at would be 11. And then if you were looking for an element greater than 11, you would search the right half of the array, and if you were looking for an element less than 11, you would search the left half. But this is an efficient algorithm. If you remember, it looks on average at log 2n items, where n is the size of the array. So if the array is large, like 1,000,000 elements, this is much more efficient than linear search. It will look at about 20 elements rather than at 1,000,000 elements. So that's a huge win. Unfortunately, we typically don't know in advance the exact size of a data set, and in addition, the data set is often dynamic, where there are inserts and deletes. For example, if we have a telephone directory, people are constantly moving into and out of a telephone directory's region. So we constantly have to insert new names into a directory and delete old names. And as we've discussed, it's very inefficient to insert and delete elements from arrays or vectors. Because let's say we want to insert 7 as a new element. It'd be inserted between 3 and 8, but we'd have to move all the elements of the array that are to the right of 7 would have to be moved one to the right, and that's an inefficient operation. You could end up moving as many as n elements. So a vector or array turns out not to be a very efficient data structure for supporting these three operations when we need to be able to have a dynamic data set. Now, we can use it in a different way, which is what we're going to do with hash tables, which is the first data structure that we'll talk about today. Okay? So, questions about where we are going? Okay. Actually, before we go there, I'm going to take a slight, what you call an intermezzo. I realized at the end of class on Thursday, I may have rushed through that final randomization algorithm from Dr. Planck, where we were randomizing the pictures in a roster. And that shuffle algorithm that I kind of went through very quickly, I felt like it was important enough that I want to give you a quick example showing you how it worked. I'm not going to repeat the pseudocode, but I am going to show you an example of how it works. The idea is that initially the pictures were numbered from 0 to n. In this case, or 0 to n minus 1. In this case, they're numbered from 0 to 6. And we want to come up with a random shuffle of these 7 numbers. And the algorithm was to start with the last element in the array and choose a random number between 0 and 6. So let's say we end up choosing 2 as our random number. Then we end up exchanging whatever is in element or bucket 6 with what is in array entry 2. So we would end up swapping 6 and 2. And now, according to the algorithm, we move to the next element in reverse order. And again, we choose now a random number between 0 and 5. So let's say we choose 4. So we end up exchanging 4 and 5. And again, we move our thing down. So next we consider location 4. We choose a random number. Let's say it's 0. So our next random number, our next random number 0. So again, we exchange 5 and 0. Move this down. So at each point, we're generating one random number between 0 and the index that we're currently at. Let's say when we're at 3, we generate the random number 3. That's fine. We simply don't change the position of 3. It stays in the same place. And we move on to 2. So we're never checking to see whether the random number is different from the index that we're at, because that's fine if we leave the element in its current place. So maybe now we end up choosing 0 again as the random number. And again, we exchange 6 and 5. And we're down to 1. And maybe for the third time, we end up generating 0 as a random number. So we exchange 6 and 1. And we're done, because when we come to the final element, obviously the only random number possible is 0. And this has randomized the set of pictures. We now go through this array and output the pictures according to this order. So as we talked about last time, that's a very efficient algorithm because we only generated one random number per iteration. Now, in both this one, I'm going to illustrate something, but back here we talked about how we want to be able to store things efficiently, and that's a recurring theme both through the rest of the semester, but it's also been a theme thus far. And I haven't really touched on how we determine how efficiently an algorithm runs. As you might expect, how efficiently an algorithm runs depends on the amount of time it takes. Okay, so efficiency equals the amount of time it takes an algorithm to run. Okay, well, you could obviously, from this definition, you might first think, well, wall clock time is the way we're going to compare algorithms. But there's a problem with wall clock time. Okay? Some of us have faster laptops than others. So if I'm comparing two algorithms, algorithm 1 and algorithm 2, and let's say I run algorithm 1 on a 2016 supercomputer, and I run algorithm 2 on a 2010 laptop. Well, even if algorithm 2 is more efficient than algorithm 1, it's possible that because we're running algorithm 1 on the faster horse, so to speak, that algorithm 1 will seem to be more efficient. So obviously, if we're comparing two algorithms, we first of all need to run them on the same machine. Okay? But even with that, there's still some other things. We would expect that the amount of input is going to have some effect on the amount of time it takes to run an algorithm. So we're often going to talk about size of the input as an important thing, and we're going to express the time to run an algorithm. This is the time to run an algorithm given the input size. So we're often trying to come up with some function. For example, last time I said that for the second algorithm where, well, actually let's do it for this last algorithm. This last algorithm, this randomization shuffle algorithm, whoops. Okay, so this algorithm that I just showed you I said that it took roughly one random number per iteration. So we say that roughly speaking, given an input of size n, it's roughly, the running time is roughly n. Now, we abstract away what we call constant time operations, and we tend to focus more on the number of iterations. We'll get into more details about this in the future. But generally, the running time of an algorithm is roughly proportional to the number of times the loop bodies execute. So in the case of our randomization shuffle, that's the loop body executes roughly n times. When we considered the second one, which was a lot less efficient, okay, that one was setting up an array that told us whether we had selected that particular random number yet. And if we had, we generated another random number, and we kept doing it until we finally got a unique one. Well, that one took roughly n times n plus 1 divided by 2 iterations. So there, we would say that t of n was roughly n times n plus 1 divided by 2, which was n squared over 2 plus n over 2, which is not nearly as good as n. So when we're comparing algorithms, we are, roughly speaking, looking at the number of iterations of their loop bodies, okay, and counting that up. And we're going for ones that are fewer. Okay? Questions about that? Okay. So, moving into hashing, let's first illustrate it. And we'll do it with something that Dr. Planck had here. So the idea with hashing is that we have something called a hash function that we're going to apply to a key. So we'll call the hash function h. In this case, we have 4 keys that we are looking to insert: Luther, Rosalita, Binky, and D'Antonio. And the idea behind the hash function is that it generates some kind of random number. So in this case, this is the random number that gets generated. And we're not yet, we'll talk about these hash functions momentarily, but for the time being, just accept that we have a hash function that takes a key and converts it to some arbitrary random number. Then, the second thing, so the hash function is kind of one component. The second component is we have something called a hash table. And a hash table is an array of some size. Again, the way we choose the size is important. We'll talk about that. But for the time being, we just care about the hash table as an array of some size. Now, based on our hash function value, we want to be able to place Luther into this array based on this value. And the way we're going to do that is we're going to take this value and we're going to mod it by the hash table size. So that will convert it to an integer in the range of 0 to size -1, which will give us an entry in the array. So this array is, how big is this array? What's its size? 10. And therefore Luther is going to map, once I mod it by 10, it's going to go into location 1. So I place Luther in location 1, right here. Okay, Rosalita is hashed to this location, which is going to end up being location 4 when I mod it with 10. And Binky is going to get mapped to location 2. Now, D'Antonio, we generate the random number, and D'Antonio also wants to go into location 1, but location 1 is occupied. So D'Antonio represents something that we call a collision. Okay, it's the third important element, is what to do when two keys want to go or hash to the same location. So those are going to be the three important elements with a hash table. Now let's just take a quick look at the three operations that I've talked about. I said we want insert. I've just told you how to do it. We apply the hash function to the key. So find, the operation is pretty simple. We apply the hash function to the key. So calculate h of key. And then B, look at that location. And it's either there or it's not there. So that's pretty easy. And delete, as you might imagine, pretty easy. Calculate h of key, look at that location, and if the key is there, simply set the array's entry to some delimiter indicate or some value indicating that it's empty. So roughly how many loop iterations do each of these three operations require? 1. They're very efficient. In fact, we call this constant time. It takes only essentially one, regardless of the size of the input. Okay, it doesn't matter whether there's 4 items in the data set or 10 million. As long as the array is quite large, it's going to take exactly one operation, roughly, to perform each of these three operations. So this is very efficient. This is wonderful. Except we do have this issue with collisions. Okay, that's not so wonderful. And we really need for that hash function to truly randomize. It really has to generate true random numbers. If it doesn't generate true random numbers, it's not going to be a particularly good, the hash functions aren't going to work very well. So for example, let's say that I know in advance that all of my keys get rounded. The book gave a good example today. When you worked the participation exercises, it said, okay, you have the price of a house. Okay, so price of a house. And they said, let's say that the function, hash function, is just the price, and we're going to end up modding it with 1,000. Okay, well, as the book points out, most housing prices are rounded to the nearest thousand, like 149,000 or 505,000. So most of them end with 3 zeros. So what do you think is going to be the hash value of most homes? 0. So we have a large number of collisions. This isn't really randomizing isn't producing random numbers. It's pretty much producing 0 for every house. And that's producing a large number of collisions. this isn't actually going to work out very well. So it's important that we choose a hash function that really randomizes things. Okay? So, as Dr. Planck says, there are three, and I just showed you, three major things associated with hash tables. A hash table, which is an array or a vector of some size. A hash function, which needs to randomize our keys, so that essentially the hash function needs to produce random numbers or produce numbers uniformly and randomly in the range 0 to size -1. And then we need a collision resolution strategy to deal with what happens when two keys want to hash to the same location. So this has actually been a fertile area of research. A lot of mathematicians and computer scientists have published large numbers of papers on hash functions because getting ones that are truly random is not so easy to do. Early on, there was a lot of research into collision resolution strategies, but at this point, it's really narrowed to 4 that we will be considering. We'll consider these 4, and in practice, only 2 of them are really widely used: separate chaining and, I believe, quadratic probing. We'll talk about separate chaining today and get to linear probing, quadratic probing, and double hashing on Thursday. Okay. So, first thing, the easiest thing to talk about is the hash table. And as the book and Dr. Planck both point out, for the hash table, we try to choose a size that is prime. Okay, just experimentally, it's kind of been shown that when the size is a prime number, that you tend to get a better distribution on your hash function. For example, back here, if we had replaced 1,000 with 1,001, which I believe is a prime number, even though all of our houses end in 3 zeros, modding it with 1,001 would give us a much better distribution of hash keys. So choosing our table size to be 1,001 rather than 1,000, it just much better randomizes it. Okay? Anytime you choose a hash table, for example, size to be even, then if you know that if the keys are kind of even, like those, then they're going to tend to hash to the even numbers. That's no good. Okay, the book gave an example of that in the participation exercises for today. So in general, odd numbers are better than even, and prime numbers are best because prime numbers don't factor. The reason even numbers are bad as sizes is because they always divide things easily by 2, and so it's easy to get even numbers only. But prime numbers tend to give you a nice uniform range. So we choose our hash table to be a prime number. Okay, so that's the first thing we try for. And then the second thing we want is that typically the size should be greater than or equal to, the hash table size should be greater than or equal to the data set size. So we can typically estimate roughly the size of the data set, even if we don't know precisely how big it is. And if we can't, we try to choose a hash table size that is bigger than any data set size we can conceive of. It's not a disaster if the size of our table is twice as big as the data set size. Okay, in fact, we'll find for some of our collision strategies that that's actually very important. And we actually will talk about the load as equal to the hash table size divided by the data set size. Actually, the opposite, sorry. It is the data set size divided by the hash table size. Okay, so normally we want the load, we endeavor for the load to be less than 1. That's desirable. Okay, intuitively, what does a load greater than 1 indicate? Go ahead. You have more data than you can fit into your hash table. So almost by definition, if the load is greater than 1, we can't store all of our data in the hash table. So that's not good. So we really like our load to be less than 1. Okay, so these are the two big considerations when choosing our hash table size. It should be prime, and the size should be greater than or equal to the data set size. Okay. So that brings us then to a discussion of hash functions. So as I said, we would like them to generate random numbers. Now, they don't have to generate numbers that are in the range of 0 to size minus 1 because we can always map the hash value into a what we call hash bucket by modding it with the table size. So we can always get the bucket number, and we often refer to a hash table entry as a bucket. It's just kind of a name that came up in the early days and has remained. So we often talk about buckets. So each hash table entry is a bucket. So the bucket number is simply going to be the hash value applied to the key, mod it with the table size. And that will produce a number in the appropriate range. So it's easy. We don't need to limit our hash function to just random numbers from 0 to the table size. As long as we have a hash function that generates random numbers, then we can mod it and it's okay. Now, there is one important feature of the hash function. How big should be the random numbers it generates? I said there's no upper limit, but should there be a lower limit? Yes. Table size. It's no good. Let's say the table size is 1,000,000, and our hash function only generates keys in the range of 0 to 2,000. That's bad because only 2% of our table is going to be loaded, right? If you can only generate random numbers between 0 to 2,000, we're never going to put anything in locations 2001 through 1,000,000. So it is, in fact, very important that they should generate random numbers that whose range is at least 0 to the table size. We don't care if it's bigger than that, but it should at least be 0 to the table size. So sometimes the hash functions are very easy. If our keys are integers, oftentimes we can just use the integer as the hash key. For example, social security numbers are randomly generated. So I'm not sure if they're randomly, but they're random enough that you can use the social security number as the hash key. So sometimes the hash function, if key is an integer, often h of k will equal key. Now, that doesn't always work out well. If, for example, with the housing prices where everything was rounded to 1,000, that might not work out particularly well. But it might when we make the table size be prime. So that would probably require some experimental use of it to see whether that was really giving us a truly random distribution or not. So a lot of times the way we discover whether something is random is we just kind of run experiments and check. Now, mathematicians have devised rather sophisticated algorithms that take a stream of numbers and render a judgment, yes or no, thumbs up or thumbs down. But you can often eyeball it and see whether it seems to be doing a pretty good job of randomizing. At any rate, if the key is an integer, often the hash key is simply equal to the key itself. That's often good enough. Like zip codes, often that's good enough. Okay? But, okay, maybe a zip code wouldn't be good enough because a lot of people actually do live in the same zip code. Same thing with telephone numbers. A lot of people, well, a 10-digit telephone number is a good key. The area code is not, because many people are in the same area code. So the full telephone number would be a good hash key, but a portion of it, like the area code, would not be a good hash key. And again, the book pointed that out. But our primary consideration is going to focus on strings, because that's the other very common things are more difficult. And this is where people have spent a lot of time. So the two most common keys are either strings or integers, and that's all we focus on in this course. And that's where most of the attention has been spent, is looking at how you convert strings to random numbers. And Dr. Planck gives us 3 examples. So the first one is by far the simplest. It takes advantage of the fact that every key or every character has an ASCII code. From 0 to 127. In fact, pretty much all randomization hash functions take advantage of this particular characteristic of strings. Every character has an ASCII code from 0 to 127. So basically, we can take advantage of the fact that we can treat each character as though it's an integer. Okay? So One possibility would be to simply concatenate them all together. So if we had Brad and let's say that B was 66, let's say R was 83, let's say A was 65, and D was 68, I believe. You could just concatenate them together to create a number. For whatever reasons, this isn't typically done. I'm guessing that it doesn't actually produce truly random numbers. One reason is that the ASCII character codes might go, in this case, from 65 to 90. I forget exactly what it is, but with 26 numbers, remember they're all contiguous, you're actually not getting a huge range, so the numbers aren't exactly random. Plus, this was just a 4-character word. If it was a 15-character word, how many digits would there be? Potentially. Well, 30 at least, a minimum of 30, because if they're in the hundreds, they could be as many as 45. And we can't represent integers that big in a computer. So that's another reason for not concatenating. So that's out, it turns out. That's not one of the techniques that's used. So a very simple technique is to simply add up the character codes. So for I equals 0, I less than the size of the string, remember strings can be treated as vectors, we simply add the value of the ASCII character code and we return it. Okay, so very simple. But also not particularly good. Remember, let's say that our table size is 1,000,000. And let's say our keys are roughly 15 characters. Do you think that what do you think is the resulting range of our hash function with roughly 15 characters? What's the upper range? We know the lower range is 0. What's the highest we could have? Yep, 127 times 15 is the highest that we could have, because the highest ASCII code is 127. There's 15 characters. The maximum value is 127 times 15, which is no greater, is roughly 0 to 2,000. I'm going to say roughly 0 to 2,000. Not very good. Okay, it's only representing 2% of our table. Now, maybe if the table was only 1,000 characters, we might be able to make an argument for it. But even then, the problem is that smaller keys that aren't 15 characters are going to cluster in the smaller parts of the range. So it's not really randomizing. So even if the table size was less than 2,000, there's still a lot of trouble with this particular hash function. Now, before we go further, I want you to observe this. This is very important. It's why one of the sections in today's reading was about unsigned integers. Hash functions typically return unsigned integers. Why do you think that is? Why do they return unsigned integers? Because arrays don't have negative indexes. Very good. So we declare our hash functions to return unsigned ints. That means that when you get the result of a hash function, you need to also declare it as unsigned. One of the biggest bugs that we will see in Lab 4 is students forgetting to declare that their variables that store the return value are getting an unsigned int. So big bug. Forgetting that the return value of a hash function is an unsigned int. Okay, and why is that? Well, let's say you have int h equals hash of x. And let's say because it can return something, it returns 1010. It's just for, we'll say some other stuff. But what's the problem now with h? It's negative. Remember that from 130, you store numbers using something called 2's complement form. And a 1 in the leading bit indicates it's negative. So if you assign an unsigned int to an integer variable, and the leading bit in the unsigned integer is 1, you will end up with a negative number. And mod's not going to fix that problem for you. Mod's simply going to convert it to a number in the range minus table size to 0. And when you try to access an element of a vector, you will get a segmentation violation. So this is really a big bad one that you need to be very careful about your return values from hash functions. You need to make sure that whatever stores the return value is an unsigned int. Otherwise, you may come to grief. Is that clear? Okay. Questions, because that's important. Okay. So moving on, here is a very popular one that actually works very well. And the way it works is that it calculates the hash values as a series of, it builds it up incrementally. So it essentially starts out with h0 equal to 53, actually h of minus 1 is 5381. And then at each step, what it does is it calculates h of I as h of I minus 1 plus, I'm sorry, it's not quite right. So we have h of minus 1 equals 5381. H of I equals 33 times h of I minus 1 plus s of I, where I is the index for the ith character in our string. And when we're done, we end up returning h of size minus 1, where that's the string size. So basically, we have an iteration over the size of the string, and at each point we multiply the previous hash value by 33, and then we add s of I. So here it is. Okay, we initially assigned 5381 to h. Why? I don't know. You'd have to ask the person who developed it, who has his initials, GJB. Then for I equals 0 to I less than the size, we have this unusual construct. Plus h plus s of I. And then when we're done, we return h. But this is probably Did you all see this particular thing in CS130, bit shifting operations? No? Okay. So this is what is called a bit shift operation. Does this operator look like any operator we know and love? Looks like something. Yes. Looks like cout. Looks like we're trying to output 5 to H. Okay, but it's not. So this is what is called an overloaded operator. When it is applied to a stream, to an output stream, less than outputs the variable's value. But when it's applied to an integer, it left shifts the integer by the specified amount, or by the specified number of bits. So you might ask, okay, what does Dr. van der Zanden mean by a left shift? Well, here's what I mean. Let's say that H was 1, 1. That was its binary representation. So 1, 1 is actually what in base 10? 3. So I left shift it. What I'm going to do is shift it to the left by 5 spaces. So I will left shift it and I will introduce 5 zeros. So I left shift it by 5 and I introduce 5 zeros. By introducing 5 zeros, that is the same, effectively, as multiplying by 2 to the 5th power, which just so happens to be 32. Okay, and it turns out to be more efficient to shift bits than it is to multiply them. So when we're multiplying by a power of 2, we actually like to left shift, because in general, when we say H left shift by n bits, that's comparable to saying, that's the same as saying H equals H times 2 to the n. A left shift by n bits is the same as multiplying H by 2 to the nth power. Okay, you can see that. If you don't believe me, think about it. So that's 1, right? 1, 0 is 2. 1, 0, 0 is 4. 1, 0, 0 is 8. 1, 0, 0, 0 is 16. 1, 0, 0, 0, 0, I'm sorry. 5 is 32. So in fact, as I add an additional 0, I'm always multiplying by 2. Yes?
Why is this more efficient than multiplying by the number? So like, why is it more efficient to do that than multiply by 32?
It's just the hardware. I'm not a chip designer, but I just know that the logic circuits required to do a shift by n bits is simpler than the than the hardware required to do a multiply. So therefore, it turns out to be a simpler, a more efficient operation. So in 130, I'm pretty sure you did design a multiplier. I don't think you designed a shifter based on what I was just told, but the logic, the circuitry is simpler for a shift operation. So that's why. But if you ask me, hey Brad, put up 2 diagrams, one for a multiplier and one for a shifter, I can't do that. I'm not a hardware guy. Okay, but I do know that. That's why shifting is preferred. But at any rate, a shift is 2 to the n. And you might ask what happens to the high order bits. So let's say, I'm just going to say that, let's say all I had was 8 bits rather than 32. So let's say that h was 0, 1, 1, 0, 1, 0, 1, 1. That was h. And now I shift it to the right by 5. Well, these 5 right here get shifted out and into what is charmingly often called the bit bucket. There is no such thing, but if you could imagine a bit bucket where bit buckets get thrown out, that's it. So these 5 get actually thrown away, and we end up with 0, 0, 0, 1, 1, and then 5 zeros in. So the 5 high order bits get shifted into the bit bucket. They're gone. They're in the trash. You might as well call it the bit trash. Trash. So they're thrown out. Okay, but I always liked it. When it was first introduced to me, it was introduced as the bit bucket. And I always liked the term, so I call it the bit bucket. So there's also a right shift operator, as you might imagine. So if I say 0, 1, 1, 0, 1, 0, 1, 1, right shift 5, then the rightmost 5 digits go into the bit bucket. And what we're left with is 0, 1, 1. And on the left end, we get 5 zeros coming in. So right shifting by n is equivalent to what? H divided by 2 to the n. So right shifting is equivalent to dividing h by 2 to the n power. Yes?
Can you right shift small numbers, or is it just going to be 0?
So good question. What if you right shift a small number? So what if the number was, that I started with, was 5 zeros, 6 zeros. So let's say I was right shifting 3. Then these 5 go into the bit bucket. Only the top 3 are left, which are all zeros. So in fact, I can get 0 out of it by right shifting. I could also, if I'm unlucky on the left shift, get 0, surprisingly. Because let's say that on the left shift, let's say the number was a very large number. Okay, this was a very large number to start with. When I left shift by 5, I get, what's the common term used for what happens when it can't represent the number because it's too big? Overflow. So this is in effect like overflow. Now it won't give me an overflow problem. It just will shift the bits to the left by 5, but the effect is by multiplying by 2 to the n, the number's too big to fit, we end up with 0. So actually a left shift of a very large number could also result in 0. Now if there was a 1 here, the lowly 1 would get promoted. Okay, so it would end up here, but we'd actually end up with a lower number than we started with. Okay, so that is bit shifting. So bottom line here is that each time we are multiplying by 32, then adding h, so that gets us up to 33 times h, and then we add si. Okay, on every exam I have bit shifting operations, and on every final it seems I also have bit shifting and bit operations. And why is that? Because you always ignore me when I say this is important and you never do any exercises with them. No one ever looks at my notes, my bit notes, and there's always a question on the exam about bit shifting and doing logical operations, and almost no one ever gets it. So then I put it again on the final. So if you really want to make sure you outperform your classmates on the first midterm, learn how to do the bit operations, okay? So I do know for a fact you learned about bitwise and or and exclusive or in 130 because, hey, you did that on like day 2 with the NAND gates and AND gates and OR gates and exclusive OR gates. So in C++, the operators for bitwise and or and exclusive or are, so if I said hi equals hi minus 1 with an ampersand something, this would be bitwise and. Bitwise or is with the pipe character, but a single pipe character. And bitwise XOR is with the caret. And what they do is what you expect bitwise and. So if h of I is 1, 0, 1, 1, and s of I were, say, 0, 1, 0, 1, the bitwise and of those, 1 and 1 is what? 1. 1 and 0, 0. 0 and 1, 0. 1 and 0. That's the result of bitwise and. Okay, bitwise or. If I did bitwise or, what's the result? 1, 1, 1, 1, because in each of the things, so 1 or 1, 1 or 0, 0 or 1, all of those involve a 1, so we get 1, 1, 1. And now the bonus question, as they say, 1, 0, 1, 1, 0, 1, 0, 1 with XOR. Okay, what is 1 XOR 1? 1, 1, 1, 0. Very good. So let's read it. We'll go from right to left. We'll go left to right. Left to right, 1 XOR 0 is 1. Then 0 XOR 1 is 1. 1 XOR 0 is 1. And 1 XOR 1 is 0. So we're just doing the bitwise, appropriate bitwise operation between the binary representation of the two numbers. Okay? Yes?
Why did they use that XOR?
There's a mistake on the web page. So that's what Dr. Plank says right here. But actually, I think it's a bug because from what I understand, the original DJB algorithm actually used plus, not exclusive XOR. So I suspect it was a bug on that person's web page. Okay, so I know this is all a bit much. So rather than plowing ahead with the last function, I'll do that on Thursday. So we'll put off this last function to Thursday because I know it's pretty nasty. And we'll switch over to the first of the collision strategies, which is pretty easy. So you'll remember that we need to figure out what to do when there is a collision. And the first approach is to basically, is the easiest, separate chaining, is why we're covering it today. So separate chaining says that we are simply going to create a list for each bucket. So each bucket is going to have a list. Okay, which will make it be a vector. And if two items collide, so let's say that here it was 0 to 9, and let's say the hash key was h of k mod 10. I know it's not good, but let's say key 12 and 32 were there. Then for 2, 12 and 32 would be on the list for 2. So basically, separate chaining says each bucket has a list, or each bucket has, a list. Implemented as a vector. For our purposes. Okay. And when an item or when a key maps or hashes to a bucket, it's added to the buckets list. So pretty simple. Yes?
So is the first element of every block empty?
Is the first, pardon?
In the index 0.
Is,
each bucket, like should the nucleus 12 in the index 0?
is it ordered, you mean? Or?
No, like it since for the when index is 2 and the index 2 0 is the
Okay, just. Why is, wait, I'm still not getting it. Why is what?
Why is like there like an empty space and then 12 and 32?
Oh, it's, I see. It's because I kind of have this notion that it's somehow pointing to a bucket. I guess it's the way I'm drawing it. I'm trying to give the idea that each entry is really a vector as opposed to being able to put something in there. I guess the better representation might have been, I know you're back there, I'll get there in just a moment. Maybe I could have done it like that, but I couldn't write everything. So maybe it would have been better to do it that way. Okay, that might have been more clear. Okay, so we will cover this more on Thursday. We have two representatives from Fast Enterprise who would like to talk to you about job opportunities with their company. So let you all take it away for the rest of the period.
Thank you. Hi guys, my name is Alana and I am actually an alum of UT, so it's great to be back on campus